Okay, so in the last class, we have stopped here at the discussion of the calculation. So today we're going to do the calculation and discuss. Hold on. 21. All right. So we've discussed the first part last week about concentration of boron atoms in the melt to be able to give concentration in the ingot of 1 times 10 to the 16. And the answer was 1.25, right? 1.25 times 10 to the 16 in the melt. So Cl is equal to 1.25 times 10 to the 16. So let's move on to the second question. If the initial load of silicon in the crucible is 60 kilos, right? 60 kilogram of silicon is used. How many grams of boron? Atomic weight of 10.8 should be added into the melt. Right, the density of molten silicon is equal to 2.53 gram per centimeter cube. Okay, so anyone has tried this question and got the answer? All right, Amiro, what did you get? So it's asking for the weight of boron. 4.25 times 10 to the minus 3 gram or 4.25 milligram. Okay. So any other answers? Any other? Paris 5.31 milligram. Okay, just right. So that's about 1 milligram of difference between Faris and Amiro. Right. Others? How about Kali? Did you try Kali? What did you get? Kali? Sakina 1.42 milligram. Okay. 1.42. Others? So we got 4.25, 5.31, 1.42 milligram. Any other? How about Izati? What did you get? Izati Shahira? 4.25 as well. Okay, we have 4.25. Kavina? 4.25 as well. Okay, we get 4.25. Right, any other? Anyone else got 1.42 or 5.31? Fakri Hadi? Max, same. 4.25 as well. Quite a number, 4.25, yeah. Akidah? Okay, let's have 4.25 to share your answers. Amiro, can you show your workout? Can you share on the screen? I'll unshare my document and then you can share yours and see let's go through, and then we go through the next one as well. Still loading on my side. I'm still seeing a loading screen.
Nampak tak, Doktor?
Still loading. Kita tak nampak. Others, can you see now? I can see now. Now I can see on the paper. Okay. Can you? Okay, I can see that. Okay, can you explain a bit? Can you go through the calculation before you get a 4.25? Okay, go ahead.
First, I find the volume of the melt using the mass and density given.
Okay.
I time and then we multiply with 10 power 16 the concentration of one cube of volume.
Okay.
And this number.
So
and
so
then
10 to the 16 is the, what is it? What is 10 16 there? What is the value of 10 to the 16? It belongs to what?
Silicon concentration.
In the ingot or in the melt?
In the melt.
In the melt. Isn't it
In the
1.2?
ingot.
Ingot or in the melt?
In the ingot.
Okay, right. Okay, go through first. 10 16 times your volume. Okay, then you get number of particles.
Yeah, get number of
Okay. Yep. Okay, go ahead.
Then we find the number of mole using Avogadro.
Okay.
Then we time with the atomic mass.
Atomic mass 10.8. Then you got 4.25. Okay, 4.25 milligram. Right, thank you. So let's see. Okay, you can unshare. Let's see 5.31. What is? Then after this, we go with Sakina 1.42. Let's see what's the difference between each calculation. Okay, explain for this.
Okay. I using the same method as Amiro, but I didn't take the 10 to the 16, but instead of I take the concentration of the melt is 1.25 and 10 to the power of 16 atoms. So that's why the answer will get 5.31.
Okay. So the rest is exactly the same like Amiro.
Yes, the rest is exactly the same as Amiro. Just Amiro take the concentration of CCS, the concentration of solid.
In the solid, okay. And yours is in the
one.
ingot. Sorry, in the melt. Sorry, in the melt. Cl, right?
Yes, that's only the difference.
So your calculation at the bottom exactly the same as well.
Yes.
Your Avogadro times all those stuff same, right?
Yes.
Okay,
But
so
use the stoichiometry method.
okay, but the calculation sequence is the same, right?
Yeah, it's just the same.
Okay, 5.31. Okay, thank you. Let's see Sakina. 1.42. Can you share, Sakina? I would like to see the difference between each. Okay, I explain, Sakina.
Okay. Can you hear me?
Yes, I can.
Okay. Oh, wait. My calculation was actually the same as Amirul, but at the end, the mass of boron in X moles, I divide that by 3 because the molecules of the boron shape, like they have three three elements. So
Sorry, what do you mean by 3 elements?
wait, I show you the
Okay.
picture.
All right, okay. So the rest is exactly the same like Amiro, right?
Yeah.
Okay.
I
Can you
divided
show
by
the
3
three?
because of this.
Okay.
Uh,
Right. Okay. It doesn't have to be divided by 3, by the way.
oh,
All right. It's okay. Okay. All right. Let me see your calculation again.
okay. Mm,
Okay. So the previous steps up there are exactly the same, right?
yeah,
Okay. So you took the concentration in the solid as well, in the ingot.
yeah, the concentration in the ingot.
Okay. All right. Okay. All right. Thank you, Sakina.
Okay.
So do you have any other answers? Ada lagi ke yang lain? Let's see first. Ada ke? Tak ada eh? Alright, so okay, let me show to you. You have to use, remember the question. Let me share with you the workout. Okay, can you see the word file on the screen? Nampak? Nampak? Okay, right, okay. So yeah, so the first one was very straightforward. We did it last week. So in the second question, read the question again. If the initial load of silicon is 60 kilos, how many grams of boron, atomic weight 10.8, should be added? Okay. When do we add boron? When and where do we add the boron? In the growth. Ditambah waktu bila? In which state do we add boron?
Bila dah melt.
Alright, bila dah melt, kita tambah bila dah melt tu kita tambah ke dalam melt kan? So we add it in the melt, right? So we add it. So basically we are adding the boron into the melt. Okay. So therefore the concentration of silicon at that time should be Cl. Okay, which is C at 1.25 times 10 to the 16 before the final ingot. So, well, the rest are exactly the same like your other calculation steps. Okay, 60 kilo, you pakai kat sini, divide by 2.53 to get the volume. And then I think that the difference is only here, 1.25 times 10 to the 16, to get the final boron atom before you convert that into the weight. Okay. Yang lain tu semua sama je, pakai Avogadro, and then the atomic weight of 2.8, and then the answer will be 5.31 milligram of boron that has to be added into the melt. Okay. So that's the thing. So that's the only difference. Okay. So I guess that's clear. So nanti saya akan add this one, upload this one on eLearn, okay? So the calculation is quite straightforward, right? The volume, mass, the density equals to mass over volume and all those stuff. Then the Avogadro number and atomic weight, quite straightforward. I think the difference is only in the 1.0 versus 1.25 thing. Okay, the rest who haven't attempted, please do so. Let me get back to the slides. Okay, so let's continue from here. Okay, can you see the slides? Please confirm, just in case. Yeah, Miro, yes. The only difference between yours is, and Faris is 1.0 versus 1.25 times 10 to the 16. So you try to go back to the calculation and plug in 1.25 to your middle step, and then try to recalculate the bottom one. Okay? Because you need to use the concentration of silicon in the melt while adding the boron into the melt. So the melt is the liquid phase, right? So last time we discussed about the two methods in the previous. Yep. So we discussed about the two ways or the two approaches that can be used in order to produce electronic grade monocrystalline silicon from electronic grade polycrystalline silicon. So remember the first step we discussed last week during the conversion of sand to polysilicon, we produce semiconductor grade or 9N. Okay, semiconductor grade equal to 9N, a polycrystalline silicon that has to go through the second step, which is the conversion of electronic grade polysilicon to electronic grade monosilicon. So 9N poly to 9N mono. And this can be done by one of these two ways, a Czochralski, CZAC, or float zone FZAC, right? And we have discussed Czochralski in the previous class. So we've discussed about the melting, the addition of boron or phosphorus. We've discussed the issue of oxygen and carbon migration into the melt and causes the final concentration to be quite high in the region of 10 to the 18 for oxygen, for example. Okay. And then we've seen how the final ingots look like. So we've also discussed about the distribution of dopant and segregation coefficient K0 equals to CS over CL, concentration of impurity or dopants in the solid versus concentration of dopant or impurity in the liquid form. Okay, and we've done this calculation today. We've discussed both of the parts. So now let's move on to the second part. That's called float zone technique. Okay, float zone or FZAC process. First one was called CZAC. This one is FZAC. So the float zone process was based on zone melting principle and was invented by Theora in 1962. So it's based on zone melting. When we say it's zone melting, so that means we are melting a localized region. Setempat kita tak melt. We don't melt the ingot in the whole crucible. Okay, kita tak masukkan dia dan melt the whole thing, but rather we melt the silicon at a specific region, okay, or zone. So that's why we call it a zone melting principle. So let's just go to the notes first before we discuss on the schematic diagram. So used to produce extremely pure silicon crystal. So it's of higher purity if you compare to Czochralski technique, right? Polycrystalline rod of ultra pure silicon. So polycrystalline rod. So the rod here on the right hand side, the whole thing is polycrystal rod, is passed through RF heating coil. So this is a heating coil. I'm gonna see later on. Yang orange ni heating coil. It's in the form of macam coil lah, neck lah, macam neck lah. Jadi buat macam tu, macam more or less C shape or in fact some condition O shape. You pakai macam tu untuk meltkan the region of interest. Okay, it's called RF heating coil, which creates a localized molten zone from the crystal ingot growth. Okay, so a localized molten zone. So if you look at the schematic diagram on the right, so you can see the whole ingot is there, but the melting is done in a localized fashion. So you can see here the ingot is there, but here is being melted at the same time. Maksudnya dia akan ada movement bila kita run float zone process, dia akan ada movement of the coil or the ingot. Dia akan bergerak dan melt the region yang dia lalu. So kalau you punya ni panjang, then dia akan melt accordingly. Dia akan melt kat region yang dia contact, yang dia dekat. So a seed crystal is used at one end in order to start the growth. So you need to have your seed. So in this case here, so you have your seed just like the way we discussed in Czochralski process, where you use your pencil size seed at the top before we start the pooling process of the ingot. In this case, we have your seed at the bottom. Okay, so the molten zone carries away the impurities, purify the crystals, but difficult to do. So while melting the crystal is actually purifying the crystal as well, because the moment it melts, it carries together the impurities from the previous zone. Okay, dia lalu kat sini, maknanya dia akan melt dan carry the impurity. So basically impurity itu akan follow the melting and it's brought to the other end of the ingot and therefore purifying the crystal at the same time. Okay. So the process is carried out in an evacuated chamber, so it has to be in vacuum condition or in an inert gas purge. Okay. So you have to control in inert condition or in a vacuum condition in order to retain the purity level. For example, if you run your process in oxygen ambient, then you are going to incorporate oxygen into the crystal at the same time, right? So there's no crucible involved, just the RF heating coil and the ingot. Okay, tak ada kawah. So expensive process only used when oxygen and carbon levels cannot be tolerated in the ingot. If the O and C are on the high side and affect the performance of the ingot, for example, the silicon we discussed last week about lifetime and diffusion length of carriers in the silicon as a result of impurities, uncontrolled impurities. So if this cannot be tolerated, then we need to do float zone process in order to further purify the crystal. Okay, this is another representation of the float zone process. So you can see here we have gas injection to inject inert gas from the upper side of the chamber. Okay, so you have RF coil keliling the ingot tu. Ingot is the blue one, vertically mounted, and then you have your RF coil keliling the ingot. So in this case, it's O-shaped kind of thing. So you can see that the RF coil is traveling. So that means in this case, the ingot is fixed in the chamber, and then the coil is actually moving across the ingot in order to crystallize the local regions and then try to purify the localized region as well. Okay, the molten region in the yellow region, in the yellow color. Okay, and then seed crystal started at the bottom. Okay, so another representation on the right, you can see the seed is at the bottom, and then the coil is moving from the bottom. So induction heating ring here is the RF coil, same thing. So it's moving and melting the zone. So bila dia naik kat tengah ni, you can see, so it's melting the zone there. That's being melted at the same time. So bila dia melt yang kat tengah ni, yang bawah ni is actually already crystallized. So region yang bawah ni, so the previous region, sebab dia gerak dari bawah, so the previous regions are already crystallized and purified, if you like. Okay, sebab dia gerak di bawah, so it's already crystallized and follow the crystalline orientation according to the seed that we use at the bottom, and then purify at the same time to produce lower levels of O and C, right? Oxygen and carbon in the final ingot. Okay, so it's moving to the center, and so in this case, these whole regions at the bottom already crystallized and purified as well. Okay, so you can see this, satu lagi gambar, the real picture. So that's the heating coil. This is the heating coil. This is the whole ingot. So it's moving from the bottom. So that means we should have our seed down here before it gets up there. Okay, so the coil is moving up and melting the local region. Sampai habis, sampai ke atas. So bila sampai ke atas, so the whole ingot is already crystallized and then it's already purified, and the impurities are pushed to the other side of the ingot. In this case, ke atas. So later on, you can see the YouTube video of animation. Right, another example. So you can see the induction coil down here, RF heating coil. So it starts at the bottom with the seed, and then it's going to go up and crystallize the ingot. So FZ crystals are doped by adding doping gas like phosphine or dibrane, depending on whether you need to use N-type or P-type. So normally if you want to use N-type, then typically phosphine is used, pH 3, or dibrane if you want to do it, if you want to get P-type. Phosphine is for N-type, phosphorus. Dibrane is for P-type, boron. Okay, added to the inert gas to form N-type and P-type respectively. So unlike CZAC process, the silicon molten by FZAC is not in contact. So it's not in contact because if you compare to CZAC, the silicon melt is in contact with the crucible. The crucible punya wall. So that causes the unintended incorporation of oxygen and carbon into the melt while doing the growth process. But in this case, the ingot is not in contact, so it's a contactless process. So the heating coil just passes through, but doesn't really touch the ingot. Okay. So it's not in contact with any substances except ambient gas, which may only contain doping gas. So doping gas is injected into the vacuum to do the doping process. So therefore, FZAC silicon can easily achieve much higher purity and a higher resistivity. Okay, higher purity and resistivity. So the doping is, if you look at this, the higher resistivity, what does it mean? How about higher resistivity here? What about, how do you comment on the effectiveness of doping in this case? Does it mean the doping is easier to do or harder to do if compared to CZAC process? Anyone? Harder to do, okay. Why is it harder? What do you think is harder? You know? Yeah, Aziz, susah. Okay, kenapa susah? Why is it harder to do in comparison to CZAC silicon?
Because
Mm-hmm.
What I call the ingot
Mm-hmm.
Is, how do you say it? Dia static. So
Okay, static, alright.
Mechanical part untuk gerakkan ingot tu
Okay.
dalam mesin float zone.
Okay, yep, dalam float zone chamber, okay.
So nak gerakkan the whole ingot through that process is
Okay,
hard
harder.
lah.
Right. So how is it compared to Czochralski process?
So Czochralski dia seed pulling tu the process melting and then apa tu seed pulling and then habis.
Okay. So
Tapi
dari segi incorporation of dopant dalam Czochralski process is, so are you saying it's easier to do?
Yes.
Compared to float zone.
Yes.
Okay, alright. Okay, thank you, Azik. Okay, any other opinions? Anyone? Float zone compared to Czochralski in terms of dopant incorporation. Hadi, what do you think? Okay, Hadi. Kenapa di higher resistivity ni float zone ni? Does it mean it's easier or harder to do? Hadi, any opinion? Or anyone else? You can just unmute yourself. Kita discuss, okay? I would like to hear your perspective. Sri, any ideas? Sri Izyani? Higher resistivity means lagi senang doping ke lagi susah doping sebenarnya? Anything, Sri? Syafiqah? Ni ada Syafiqah? Senyap ya semua ni? Kali? Are you there? Yeah. Okay, Kali, what do you think? Is it easier to do or harder to do in comparison to Joukowski process? Kalau tengok logik lah, just tengok logik. Lagi senang ke lagi susah nak dope silicon in this case? Okay. Juara cakap lagi susah. Kenapa? Juara? Why do you think it's harder to do in this case? Harder to dope, okay. Kenapa tu? Why is it harder? What is the state of silicon? Okay, contactless. Yep. Yeah, one reason is contactless. So kalau you tak ada contact, susah sikit lah nak dope kan. Okay. So if you compare that to apa ni? Joukowski, for example, is in contact, isn't it? Sebab you incorporate the boron or phosphorus into the melt. Macam masak masuk ni kan, masak gulai kemudian tambah gula. Tambah garam ah. Tambah garam. Dan you kacau kan? Senang kan? Kacau dalam melt. Kalau yang ni kita tengok macam ni the ingot is ready, isn't it? What is the state of ingot? Solid kan? Kalau benda dah siap, you nak tambah others, it will be more challenging, isn't it? Even though you do local melting in the ingot. So gas will be in the ambient, phosphine ataupun dibray will be in the whole chamber here, will be injected into the chamber. But then, if you compare this to Joukowski, you are doing the melting of the silicon by regions, localized region. So in comparison to you the melt, then you just add and macam kacau lah. Then that will be a lot easier to incorporate. Okay, that's why the fluid zone process results in higher resistivity wafers. Okay. So additionally, multiple zone refining can be performed on a rod to further reduce the impurity concentrations. So that means you can do multiple times. Okay, multiple zone refining can be performed on rod to further reduce the impurity concentration. So we know that when we are doing the zone melting process, guna RF coil, so dia dah push the impurities to the upper side, isn't it? But you can do multiple times if you want to further purify, but that comes with a added cost. Okay, segregation coefficient plays an important role. Cannot boron has an equilibrium segregation coefficient of 0.8. We discussed this one last time. Phosphorus has 0.35. Therefore cannot only be segregated but also evaporates from the melt at a fairly high rate. So phosphorus also evaporates from the melt at fairly high rate. So that means it's a lot harder for you to get the intended concentration of phosphorus in the solid with whatever you put into the system during the fluid zone process. Okay, so you kena letak lebih lah basically in order to get the intended concentration level. So this is the reason why on the one hand it's easier to produce more homogeneous p-type than n-type. Okay, so therefore due to this evaporation of the phosphorus at quite a high rate, so it's a lot easier to get homogeneous p-type. That means using boron if you compare to using phosphorus, because phosphorus suffers from the evaporation issue. Okay, evaporation at higher rate. So boron is much lower than. Okay, so it's a lot easier to control the p-type process with boron in comparison to n-type process with phosphorus. Okay, so that's why we discussed last time in our previous class about the doping uniformity along the ingot for n-type wafers, where you cannot use most of the ingots that you've grown in the Joukowski process, for example, with n-type. Okay, you akan ada issue on n-type because you need to chop off more regions that need to be remelted for another growth process due to non-uniformity issue. But this is not happening in p-type because it's based on boron. So if you compare CZAC and FZAC processes, So CZAC allows a big crystal diameters up to 10 to the 18 at the moment, not 10, 18 inch, 450 mm. So you've seen the wafers when we first discussed the cost, yang besar tu, 450 mm or 18 inch, compared to FZAC and lower production cost per wafer for CZAC, right? So CZAC is cheaper compared to FZAC. So disadvantages of CZAC process: high impurity incorporation, oxygen up to 18, carbon up to 18. From the quartz and crucible, graphite crucible, daripada kawah tu, due to the contact process, contact based process, which lower the minority carrier diffusion length in the finished silicon wafers. Okay. Minority carrier diffusion length, we discussed this one last week as well. Remember, if you have more impurities, if you have more of this O and C, then the tau will be lower. As a result, the L will be lower. So minority carrier diffusion length in the silicon wafers or in the device eventually will also be lower. Low homogeneity of the axial and radial concentration in the crystal caused by oscillation in the melt during the growth. Okay, so radial ada uniformity issue if you go away from the center part. So this makes it difficult to attain high ohmic CZAC wafers with resistivity above than 100 ohm cm. So MCZ can retard these oscillations and improve the dopant homogeneity in the ingot. So MCZ can not only helps to reduce the incorporation of oxygen and carbon into the melt, but also improve the homogeneity of the ingot during the growth process. So FZAC, on the other hand, very low impurity concentration in the silicon crystal because we do the zone melting process and you carry the impurities away from the active region. Kita push dia ke atas and chop off the final top part. Okay, so it's out of the equation. So in particular, oxygen and carbon concentration are much lower as compared to CZAC, right? O and C are much lower compared to CZAC, since the melt does not come into contact with the quartz crucible and no hot graphite container is used. So because we only use an RF coil, non-contactless, in a contactless process. Okay, so tak ada sentuh, so therefore less contamination in that sense. So dopant concentration in the final crystal is more homogeneous, which allows very high ohmic wafers as well as wafers with narrow specific electrical resistivity. So if you, siapa pernah pakai silicon wafer during your FIP? Anyone? Anyone has used silicon wafers? Ada ke? FIP ada pakai silicon? Ada, semua tak buat silicon. Ada? Ada, right. So kalau you ambil silicon daripada lab, so there is like a set. Dalam tu ada 25 wafers. 2 inch. Right, 2 inch diameter. So dekat atas ni ada label. Label resistivity. So rho equals to berapa? Say 1 to 10 ohm cm. So this is the resistivity range. Okay, range of resistivity of the wafers 1 to 10. So it's a lot harder if you're talking about growth process. So it's a lot harder to do to make sure that your resistivity across the ingot to be 1 to 3, for example, 1 to 3 ohm cm is a lot harder to get if you compare to 1 to 10 ohm cm. Contoh, sebab this one is a lot tighter, isn't it? 1 to 3 ohm cm, that means throughout your 2 meters ingot, for example. So you can only afford to have resistivity variation between 1 to 3 ohm cm. Sepanjang 2 meter tu. Maksudnya kalau you chop off dekat top, you are sure that the resistivity is 1.1 ohm cm. For example, you chop off somewhere in the middle, you are sure that it's perhaps 2.1 ataupun anyway between 1 to 3. But the variation is very small. On the other hand, it's a lot easier for you to get 1 to 10 variation. Lagi senang nak control lah. Maknanya you can just get quite varying properties of the resistivity across 2 meters. Kalau you nak compare dengan 1 to 3. 1 to 3 means you punya spec you punya spec limit ni, kalau you control dalam you punya proses. So we talk about SPC last time, statistical process control. Katalah you punya target, center target is 2 ohm cm. For example, kalau you buat you are the engineer for the Grafsky process, and you can afford to have variation of plus minus 1 ohm cm. Okay, maksudnya the highest you can go is 3, the lowest you can go is 1. So your variation is only within 1 to 3 ohm cm, centered at 2 ohm cm. On the other hand, so yang case pertama ni, 1 to 3 ni is a lot harder to control because the process specification is very tight. On the other hand, if you want to control 1 to 10, for example, kalau you ambil chart belah kiri tadi, you compare to 1 to 10, so you can afford to have this much variation, isn't it? So maksudnya you punya center kat sini mungkin around 5 ohm cm, then you can afford to have a variation of plus minus 5 or plus minus 4 lah contoh. So you can go up to 10 maximum, and it can be 1 on the minimum side. Okay, maknanya process control there is a lot easier to do. So kalau you want to go for your internship or your job later on as a process engineer, so this is one of the things that you're going to be doing to maintain the process, to sustain the process, so that the results are within or always within the spec limit ataupun the control limit. And that's called SPC, statistical process control. Right? So FZ disadvantage, more expensive than CZ, and the crystal diameter is limited to 8 inch, 200 mm. I'm not sure about the current capabilities of FZ. Perhaps we have got a bigger diameter system for the recent FZ process. Okay, so silicon doping, we discussed this one during our 386 class. So we can either grow your silicon ingot to be completely intrinsic. Okay, your ingot yang you grow from either CZ ke FZ ke, it can be, say that's the seed to be chopped off, nanti kita akan chop area ni, chop this area, so this will be the active area eventually. So you can have this ingot completely intrinsic, which is undoped, so that means tak ada dopen. So do you remember what is the intrinsic concentration of carriers in silicon from our previous course? What is the Ni value of Ni value in silicon? Anyone can recall? If you do it intrinsic, not extrinsic. Anyone can recall the magic number? Sakinah, 10 to the 20. Okay, Sakinah, 10 to the 20. Anyone else? Remember the magic number before we did the law of mass action last time, NPN squared? Remember what is the value of Ni in silicon? Anyone can recall? Come on, magic number before I finish the class. How many more pages do we have? Habis dah, last page, huh? 1.12 what? 1.12 is the band gap, right, Amiro? 1.12 electron volt. So this one is Ni, the intrinsic carrier concentration in silicon. So anyone can recall? Okay. So 1.5 times 10 to the 10, right? Or the other one, what is it? Hari tu kita discuss about two values, right? You can use either one for your calculation. It can be 1.5 times 10 to the 10, or the other one is, what's the second magic number? 10 to the 10. Satu lagi? Ya ke 2.0? 1.0, right? Remember, Ni squared tak payah kira ada yang depan tu. You can either use this one. So if you grow intrinsic silicon ingot, so your final Ni will be 1.0 or 1.5, either one is fine, times 10 to the 10. So that's the level of intrinsic carrier concentration if you don't dope the ingot with phosphorus or boron, right? So that's why the 386 course is important and related to this. It serves as the basic for this course. On the other hand, if you dope your ingot to be N-type, you need to use pentavalent atom like phosphorus from group 15 or arsenic or antimony. Okay. On the other hand, you can also dope it to be p-type, group 13. Boron is the common one, gallium, aluminium. Okay. And if you look at the table here from the left to the right, so it shows the level of doping in the silicon during the growth. Okay, new info yang you akan pakai eventually, right? So the doping level may vary from intrinsic to as low as 10 to the 14 for lightly dope. So if you use lightly dope wafers, that means concentration is about 10 to the 14 centimeter cube, right? Centimeter minus 3 per centimeter cube. So this is called lightly dope. So or you perhaps you're using 10 to the 13 ke ataupun early 14. So it's considered lightly dope. So therefore we label it as N++, sorry, N minus minus or P minus minus. Okay. Tengok kat subscript kat atas tu. And if you increase the doping level a little bit to be lightly doped, so that means the ingot or the wafers eventually will be in the region of 10 to the 14 to 10 to the 16. And we call that as lightly doped. So the notation is N minus or P minus depending on the polarity. Okay. So the typical doping level is between 10 to the 16 to 10 to the 19. Okay, kita pakai N atau P ya, tak ada plus, tak ada minus, right? So if you do heavy doping on the ingot, on the wafers, so beyond 1019, so 1, 2, 1019, 3, 1019 onwards, so we're going to use N plus. In some cases, if it goes too heavily, then some people even use N++, P++. Okay. So you're gonna see this one later on. The moment we discuss about the fabrication of the device, of the IC, of the solar cell, of the IC. Later on, you're gonna see that some regions are doped to be N+, P+, and then some other regions are intentionally doped to be N++, P++, and some other regions are left to be intrinsic, okay, depending on the device design. Okay, so and we discussed this one last time, so I don't want to go through it again. N-type and P-type. Right, so yeah, that's all for today. Do you have any questions on CZAC, FZAC, or the doping? Is it okay so far? Can everyone follow? Okay, yeah. All good. Easy, right? Still easy, right? Oh, so good. Oh, so far too easy? No? Tak easy, kalau too easy for now. Okay. Can go. Okay. Can go. Okay lah. Can go. Right. So I'll see you. Tomorrow 11 to 12, right? Okay. Tomorrow another 1 hour, 11 to 12. Then Friday for 2 hours. Okay. I'll see you tomorrow then. Bye bye. Assalamualaikum. Take care.
Thank you, Doctor.
Welcome. Bye bye.